For our first reaction, we are going to take cyclohexene and we're going to react it with HCl. Now, usually what we do with these arrows is we put reaction conditions. Usually the reactions that are in excess, and over here are the organic reactions. So this is just a reactant, and we are going to see what happens when we take cyclohexene and treat it with HCl. Well, what happens, it's an addition reaction, so this adds to this. One H goes to one end of the double bond, and the Cl goes to the other, and you end up making chlorocyclohexane. Now the mechanism tells the story. Every single bond-making and bond-breaking event gets an arrow. So if we remember the pi bond here is not as strong as all the other bonds, so it will break and pick up that H. Now there's a bond between this H and this Cl, and those electrons end up going toward the chlorine. What we usually do is draw the mechanism as a half circle under the reaction. So now we look at what we've just done. One of the H's, or the H ended up on one side of that double bond. I'm going to draw in the H that was already there. There's an H that was already there that we didn't draw, and we just formed a carbocation because we added an H+. We also draw these equilibrium arrows to say that this reaction can just as easily go backwards. And we also have a chloride. Now the next arrow links the chloride minus with the carbocation plus. This is a nucleophilic attack. And that completes the mechanism. Just a two-step mechanism where the pi bond breaks and goes toward the electrophile and the chloride makes the new bond. Well, this reaction was fairly easy because both sides of the double bond have the same substitution, the same number of carbons attached. So if I take one methyl cyclohexene and I do this reaction with it, HBr, HCl, both the same, I have two possibilities. I could make and put the bromine on the tertiary carbon, or I could put the bromine on the secondary carbon. And we need to be able to decide whether it goes here or here. Well, this is why we learned about carbocation stability. So let's draw the arrow first. Doesn't change from the first reaction. And we have two possibilities. Either the H added to carbon number 2 right here, and again I'll draw in the H and put the carbocation on carbon number 1, or the H added to carbon number 1, I'll put the H in, and the plus is on carbon number 2. Well, from our previous discussion, we know that this is a much more stable carbocation than this one. So this is the one that works. This one does form, but it's a minor product. This will be the major pathway. So the bromide comes in. I'm not going to switch to a red arrow. It's sort of tedious. And adds to the plus charge. And we'll make that structure right here. This principle has a rule, a Russian name, Markovnikov. Markovnikov's rule says that the H plus, or whatever adds first, will add to the less substituted side of the alkene. So I highlighted Markovnikov's rule that we developed with the addition of the HCl. Now, let's talk about adding water or hydration of an alkene. If I take cyclohexene or 1-methylcyclohexene and try to add water to it, I'm going to write it as HOH. What will happen is this is just not acidic enough. pKa is 16 to add to the double bond. So this would be a no reaction. What we need to do is add a catalyst. Catalysts speed up reactions and not changed in the process. Now the catalyst that we're going to add is H3O+. It's just an acid catalyst. So this is acid catalyzed hydration of alkenes. So how do we make H3O+? Well, any strong acid, when it's in aqueous solution, produces H3O+. Now when you go to college, your professor might write H2SO4, but I'm going to write hydronium, H3O+, because the focus of this class is learning mechanisms, and H3O+ just makes it simpler. Realize it comes from H2SO4. Now, the process will be similar to what we've seen before, and it will follow Markovnikov's rule, where the H will go to the less substituted, and the OH will go to the more substituted side. Now, if we draw the mechanism, remember you always use your catalyst first. So I'm going to draw out hydronium, and the pi bond breaks, goes to pick up that proton, this bond breaks, and these electrons end up on the O. We are making water right here. Now we have a carbocation at what was carbon number 1. We also have two waters, one from the reactant and one from the catalyst. Doesn't matter, water is water. Here's the nucleophilic attack of the water on the carbocation. Now that water stays together, so right now we have 3 bonds to oxygen, so it has a plus charge. The last step is we need to reform the catalyst. We use the other water to come and pick up that proton, deprotonating the alcohol to form the product. So remember, use the catalyst first and then make the catalyst last.